So next, we have Roberta Paladini from Caltech IPAC, who will be talking about the Milky Way as the Redshift Zero template to investigate star and planet formation.
Hello, hi everybody. Hopefully this is working. So thank you to the organizer for giving me the opportunity to talk about this white paper that was submitted recently, just a couple of months ago, to describe new ideas for the galactic plane survey with Roman that now we know it's going to be a reality. And in particular, today I'm going to focus on, if I can see. I'm going to focus on star formation, and before doing that, I want to just acknowledge all the co-authors that participating in these white papers, and in particular, I would like to call out a few people like Etienne Bachelet and Wang Lim at IPAC, and Sergio Molinari at INAF. Tom McGaff at University of Toledo and John Bally, University of Colorado, Adam Ginsburg at University of Florida, and Cara Battersby at University of Connecticut. So I'm going to give away a little bit the end of the story since the beginning, but what I want you to really the take-home message here is that science cases for projects can evolve over time. So when we started talking about the Galactic Plane Survey many years ago, the science cases that were described in the W1st interim report in Green et al. 2012, and they were then reprised in the white paper that we submitted in 2021, that are pretty much exactly the same. Those science cases were really centered about galactic structure. And at the time, this was really, I would say, a very major concern for the galactic community. I would like to remind that the white paper that was submitted in 2021 was submitted before, I think, a major event in astronomy. And the major event was the launch of James Webb. And that happened in December 25th, 2021.
T-minus 30 seconds to count.
So I think this was really, again, a gift, a Christmas gift to the community.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
Is it start?
Décollage.
Décollage, liftoff from a tropical rainforest.
So why do I say that this was such a revolutionary?
30 seconds to count.
Why do I say that this was such a revolutionary event for galactic astronomy in particular? There is one program, and I want to emphasize I have no affiliation whatsoever with this program. It's the FANGS program, which is the physics at high angular resolution in nearby galaxies. In FANGS, the PI is Eva Schinnerer, MPI in Germany. It's a program that also observes many galaxies from ALMA to, with many data from ALMA to VLT and HST. And there is then a subset of these galaxies that have been observed by James Webb and the PI's Janis Lee Space Telescope. And you can see here a composite of images of these 19 galaxies that are between 5 megaparsec and 25 megaparsec. And we can see here the beautiful images that have been generated by James Webb. And what you can see straight away is the level of detail that we can now get from these galaxies. In particular, what you can observe is that we now have an unprecedented view of the structure of the galaxy that we have never had before. We can now basically, galactic and extragalactic community talk the same language for the first time in history, basically. So we can see filaments, we can talk about star formation. I've been an galactic astronomer for 20 years, and this is really the first time that galactic and extragalactic community can talk the same language. However, so before I switch to the next point, I want to say, so this to me has been like also kind of existential crisis, because, okay, so now what is now our role as galactic astronomers in this new James Webb era? What is our role as galactic astronomers now? And I think as galactic astronomers now, what is our role is really to put our galaxy in this big picture where we need to use our galaxy to build the ladder from the Milky Way all the way to the high Z galaxies, going from Milky Way, the local volume, to the Fangs galaxies, and again, all the way to high Z. So basically, see what we can do in our galaxy that we cannot still do in external galaxies to help this picture of galaxy formation and evolution. So we have to get out of our small picture in which we have confined ourselves for decades. So, okay, what Roman can do now? Roman, I think, can play a unique role because Roman can do something that we cannot do in any other galaxy. So Roman is an extremely efficient star finder. And the thing is that we can see with Roman all types of stars. We can see young stars, main sequence stars, and evolved stars. And this still we cannot do in external galaxies. Yeah, we can do this a little bit in the LMC, in the SMC, maybe in M31 a little bit, but we cannot do this certainly in the local volume and beyond. We will have to wait until the Habitable Worlds Observatory in 2040 and beyond, where the bigger apertures will allow us to do this. But until then, that's basically what we have. So I want to go back to young stellar objects. First of all, I think there is a little bit misunderstanding. Sometimes people say that with Roman, we can look at nurseries of stars, and I don't think this is correct. We cannot see with Roman anything younger than 0.5 mega years, but we can definitely see very clearly class 1, 2, and 3. And I did this very quickly, this diagram, because I think it's very important to put again Roman in the bigger picture of what is available today. So Gaia was extremely sensitive to class 3 young stellar objects, a little bit more evolved class stellar objects, although we know it was limited by extinction. So in terms of number of detections, it was limited to our solar system. Roman, again, we see class 1, 2, and 3 because of the bigger wavelength coverage. But then if we want to go to the real stellar nurseries, then we have to go to Spitzer and Herschel. Spitzer and Herschel's in number of detections were limited by the angular resolution. But again, if we want to have the whole picture, then that's where we have to combine all these wavelengths. But again, in terms of detections, Roman will be really a breakthrough for young stellar objects. Now, the beauty of the stars, having all these stars, is that each of these classes can actually provide us with a very specific information about our galaxy. So the red giant stars, or red clumps, provide us an information about the structure of the galaxy. And I will come back to this point in a minute, because I just said, well, this is not so relevant anymore. Yes, it is relevant, I think, in a different way. Then there are main sequence stars, and then there are the young stellar objects. So these are the kind of science drivers for star formation that we put together. And we think that basically we can go all the way from the very large picture to the very small one. So from the very large scale of the entire galaxy to the very small scales. So we can look at the structure of the galaxy and try basically to understand what is the role of spiral structure with respect to star formation. So how do they affect one another? What is the role of the black hole for, again, star formation? We know now in external galaxies that there is material accreted from the circumgalactic medium into the black hole, and then there are outflows, and we want to understand this cycle. There are star and cluster star formation rates. External galaxies are basically only sensitive to massive star formation. In our galaxy, we can see both low and high mass stars. We can investigate the initial mass function. We can look at dust evolution and especially grain growth, and look at how stars really start and planets also grow. And then we can look at the physics of feedback. And we know now that slow feedback is extremely important for star formation. So just a word about initial mass function. So which is one example I want to give you. So this is a fundamental question that has been going on for decades. Still, we don't know if the initial mass function is universal or not. Now, we know that up to 1 solar masses, all the models that are out there are pretty much consistent with each other, but at masses below 1 solar masses, you can see that there is a very high discrepancy between models. And in addition, there is also the question whether from star formation to star formation there is a consistency between functions or not. One of the major problems has been to resolve stellar binary systems. Until now, we didn't have the resolution to solve this problem. Now we have this resolution, and we Roman, and we can solve this problem. So we have identified, for example, a region like the Serpens in the Aquila Rift, where we can tackle all these questions. This is in the white paper. We basically suggest that we could cover a region which is covering the spiral arms up to the tangent points in the 1st and 4th quadrant, so plus and minus 30 degrees. This is the tangent point to the bar and the tangent point to the Scutum Sagittarius bar. And this extended box here includes the bulge and also the Serpens region that I showed. And there is a science traceability matrix for all the science cases I showed that basically describes what would be the best choice of filters and coverage, cadence and dithering and so forth. The last thing I want to show, because I know that the time is up, is that there is definitely a complementarity between Roman and other facilities, for sure Rubin, but I cannot not mention Spherex, on which I spend a lot of my time on. Spherex, in particular for star formation, will generate 9 million spectra, absorption spectra of regions of star-forming regions, in particular ICES. So again, the combination, most of these will be in star-forming regions and on the plane. So the cross combination of all this information will be really unique for star formation. I will stop here.